In this video, I will show you how to create a snow shader that implements one fairly unknown, almost secret technique that experts use to achieve an extra level of realism. This advanced snow shader will support gradual appearance over time, provide an enormous amount of detail, and seamlessly blend with the surface of the mesh. So let's get right into it. The first step for creating a realistic snow shader is to set up a proper PBR shader. This will serve as a base look for the parts of the object that aren't covered by the snow. We can start by creating a new HDRP lit shader graph and double-clicking it to open it in the editor. Since the base of the snow effect is a classic PBR shader, I will skip the creation and just quickly go over the final result. The shader extracts the color from the base color texture and applies the normals from the normal map. For additional flexibility, the shader exposes the strength of the normals as an external parameter. Finally, it uses an additional mask texture that has ambient occlusion and smoothness packed in the green and alpha channels. Those values are then unpacked and provided to the output of the shader. If you want a separate video that goes deeper into the specifics of PBR shaders, make sure to let me know by leaving a comment down below. And this is how the scene looks with the basic PBR shader applied to the asset's materials. It looks pretty realistic, especially from a distance, but we're here to create a snowy environment. So let's start with the creation of the snow effect. The second step is to show the snow texture on certain parts of the object. But how can we specify where to show the snow texture and where to show the original color of the object? The basic principle of snow effects in shaders is to blend the snow color with the current color of the material. The blending is based on the angle of the surface. This mimics the realistic behavior of the snow accumulating on top of the surface. The amount of snow is determined based on the angle between the surface normal and the world up direction. If the angle between the up direction and the normal vector is less than some threshold, we display the color of the snow instead of the original color. If the angle is larger than the threshold, only the material's original color is visible. Finally, instead of specifying the hard angle threshold, we can specify the minimum and maximum angle limits. These angle limits will create a blending zone, where the snow color will smoothly transition to the color of the material. Back in the shader graph, I've prepared a node that does just that. It calculates the influence of the snow based on the provided normal vector. Also, it uses planar texture mapping to sample the snow texture based on the world position of the mesh. If you aren't familiar with the planar projection and planar texturing techniques, I've made a video that explains them in detail. You can find the link to it in the description. In order to use the snow influence node, I've created a couple of properties that we're going to need. A snow color texture for sampling the color of the snow, a smoothness parameter for overriding the smoothness of the snowy patches, and a tiling factor for the color texture. Finally, I've added two additional properties. One that will control the amount of snow we show on the object, and the other that controls the threshold of the gradual blending zone between the snow and the color of the mesh. Instead of using the color of the base texture directly, we need to blend it with the color of the snow based on the angle of the surface. To calculate the influence and the color of the snow, we're going to use the snow influence node we've just seen previously. We can now plug in the snow influence as an interpolation factor between the snow color and the base color of the mesh. I've also added a little smoothing for a nicer effect. Let's see how this looks. Well, this resembles a snow cover, especially when we look at it from a distance. But if we take a closer look, we can see that the effect isn't that realistic. We've just recreated the basic snow shader that I see in most indie games. It's simple and effective when we look at it from a distance, but the illusion breaks when we look at it up close. To improve it, we can make a simple change when calculating the influence of the snow. The third step for creating a realistic snow shader is to calculate the snow influence using the normals from the normal map instead of using the normals of the mesh. To do that, we need to transform the normal from tangent space to the world space. We can use the transform node for that. Just set the transformation properties to go from tangent to world space and the type to be normal. Then, we can use that normal when calculating the influence of the snow. With that simple change, we get much better results up close. Let's compare them with the previous state to see how much of a difference this makes. Most of us would be satisfied with this look due to the massive improvements made by using a normal map for snow calculations. But following this logic, what if we could use even more detailed normals when calculating the snow cover? Adding more details is done by overlaying additional details normal map over the main normal map. The purpose of the details normal map is to show those small bumps and crevices when looking closely at the object. It needs to be seamless because it will be tiled across the surface. But this is where a large issue occurs. How can we correctly blend these two normal maps? Also, when the snow amount increases, the surface of the snow should have different normals from the ones of the underlying mesh. And these snow normals should be sampled by using a planar mapping technique, which poses an additional issue for blending. The solution for this problem was found by Unity engineer Morten Mikkelsen. He published a whole paper about this 4 years ago, presenting a technique called surface gradient-based bump mapping. I won't go into the inner details and mathematical expressions of the paper, but he basically presents a modern framework for correctly combining influences of multiple normal maps. The way to do that is to calculate what he calls a surface gradient, which then enables us to linearly combine influences of different normal maps. The surface gradient is a projection of a regular height gradient onto the tangent plane at a certain position of the mesh. And yes, you see it correctly. Mikkelsen is such a boss that he can reference his previous papers in the current ones. Since this probably feels overwhelming, as it certainly did for me when I first stumbled across it, let me simplify this a bit. What Mikkelsen is saying is that if we manage to calculate this surface gradient for each normal map, we can then easily add or subtract these surface gradients and get the final result. Well, perfect, this is exactly what we need. The real question now is how can we calculate this surface gradient? Mikkelsen explains that if we know the tangent and bitangent vectors in world space, we can use the derivative of the normal to scale and add them together to get the surface gradient. That's awesome, but how do we calculate this derivative now? Well, Mikkelsen did the math and came up with this formula. He was also generous enough to provide a code snippet that implements it. With that, we have everything we need to recreate this in the shader graph. And that's exactly what I did. I followed the paper and Mikkelsen's code snippets to recreate everything we need. I won't get into the details of everything, but there's a link to the project's repository in the description and another link to Mikkelsen's paper, so you can check that out if you want. However, I would like to mention this surface gradient from normal map node that we're going to use directly in our shader. This node calculates the derivative from the provided normal map, generates tangent and bitangent vectors, and uses them to calculate the surface gradient. We can then use this surface gradient and add it with others or resolve it to a final world space normal vector. So, back in our shader, we need to add 3 new properties. Texture 2D property for the details normal map, and 2 float properties, one for defining the strength of the details normal map, and the other for specifying the tiling. Now, let's remove the current way of calculating normals since we don't need it anymore. Then, we're going to use the surface gradient from normal map node to calculate the surface gradient vectors for both the base normal map and the details normal map. Finally, we're going to compose them together by using the surface gradient compositor node. This is just a helper node that provides a convenient way of adding multiple surface gradients together. After combining them together, we need to transform the surface gradient back to a normal vector. This transformation is called the resolve. It's very simple. We just need to subtract the surface gradient from the normal vector in the world space and normalize the result. Finally, we can use the resulting resolved normal for calculating the influence of the snow. And we can also plug it into the output normal slot of the shader. Just make sure to change the fragment normal space option in the graph settings to world instead of tangent. Let's hop into the scene and see how this looks. We got some nice details on the snow on the sides of the rock, and the whole snow coverage across the scene looks a bit more detailed. We can compare it with the previous state to see how much more detail this version has. No wonder AAA shaders look so much better compared to the regular ones. You're still watching? This means you've managed to survive the math onslaught, so congratulations on that. If you want to enrich your winter scene with snow particles, make sure to watch this video. It will show you a step-by-step process of creating snow particles in Unity by using the visual effects graph. Also, if you think you learned something from this video, please leave a like, it will help us a lot. Thank you for your time and good luck with your creations.